We're ready for lecture number 28 by Jim Hendershot. The topic of this is the PM synchronous design theory for surface PM and internal PM rotor types of brushless motors. The inner, outer, or axial surface PM motors the back EMF of these is seldom sinusoidal. They're usually sort of flat topped. The magnet shapes can be arc shaped or bread loaf, and actually the magnets can be shaped a bit to try to make them sinusoidal. These machines are driven by 6-step drives, what's called as 6-step. That says 6-step. It's supposed to be 6-step drives. And that results in 120-degree electrical degree commutation. A unipolar drive means that it only produces current polarity of one polarity, and that requires 3 transistors, and only 1 phase produces torque at a time. 1/3 of the copper is utilized for producing torque and power. There aren't very many 6-step brushless DC motors driven this way. The most common is a bipolar drive with 6 transistors, the same bridge connection as an induction 6-transistor bridge, 3-phase bridge, with 2 phases producing torque at a time, where 2/3 of the stator copper is utilized to link with the rotor flux. The stator designs typically utilize phase coils placed around single teeth, but not always. Commutation requires some sort of a shaft angle feedback sensor to tell the stator gate drivers when to fire the coils or when to disconnect and connect the coils to the DC rail voltage to produce the peak maximum amount of torque. And the speed is proportional to the DC voltage, not frequency. Now the PM AC machine, as opposed to the PM DC machine, they're really the same motor, but the name got changed because of the way they're driven. The IPM motors, or inner mounted magnets, internal magnets, that's what a lot of these are. You can drive a motor with a AC drive and call it a PM synchronous machine, whether the magnets are on the surface of the rotor or whether they're on the inside of the rotor. That's what this says. The sinusoidal back EMF is usually required with minimum harmonic content. The surface magnet configuration can be arc-shaped or bread loaf. The internal magnet shapes are usually simple rectangular slabs or blocks. The sinusoidal driven motor can be driven with hysteresis control. The important thing about this sine wave control is its commutation is full commutation of all 3 phases all the time with 6 transistors, and all 3 phases produce torque, and 100% of the copper is utilized for producing torque and power, as opposed to the PM DC 6-step version where only 66.66% of the copper is utilized for producing torque. This drive scheme also requires shaft position, the pole location on the shaft or the rotor position feedback. This can either be done sensorless or with sensorless. You can field-oriented control of the current with D-axis and Q-axis control can be used as an alternative to hysteresis current control, and in fact the the D and Q axis current control has become the most popular these days. The 6-transistor bridge allows all 3 phases, as we said, to produce shaft torque, and the field-oriented control can be sensorless or because of as long as the circuit has enough difference between the D and the Q axis inductance so that it can be measured, then you can have a very good sensorless scheme. There's other sensorless schemes that use an open loop startup routine and use back EMF to determine rotor position, but those require a little startup procedure. The stator designs are typically designed to facilitate sine-shaped back EMF with one or more slots and coils per phase. The skewing of the rotor or the stator or the magnet poles themselves, shaping to make the air gap, vary the air gap, helps a lot for sinusoidal back EMFs as well. Here's what the back EMF comparisons look like for an ideal sine from terminals A to B, B to C, and C to A. These are all perfect sine waves, but the ideal trapezoid back EMF looks like this, quite square. Very hard to shield. Reality is somewhere in between for most machines. The circuit voltage equations for constant phase inductance are given by these equations here. The flux linkage equation, the voltage equation, and the it's not necessary to use these equations for the initial design process. A simple back EMF equation can be used for sizing the design for effective turns, but an FEA analysis is used for final machine design analysis, particularly the IPM types. You don't need to use FEA for the 6-step motors to actually predict performance, except for cogging torque. You need FEA for that. The voltage and torque relationships for PM brushless machines is a very important topic. The industry has defined these two parameters in terms of a torque constant or a voltage constant, and for PM brushed servos is where this came from. PM machines that have the same flux linkage characteristics in the air gap as the brushless. It's just the commutation and the control of the windings is the only difference between the machines. So the relationship between the torque per amp, Newton meters per amp, and volts second per radian or volts per radian per second, these are, for a DC servo, these are exactly equal. Numerically, this is the same number. But for a brushless machine, they're close, but they're not exactly equal. If the voltage term is defined as peak, then they're pretty close to being the same. But otherwise, they're not the same if you're going to compare them in terms of their mean or RMS values. So and sinusoidal voltages are usually expressed in RMS values, not peak. But if you look at this, if you have a copy of this book, this ISBN number given there, Design of Brushless Permanent Magnet Machines, in Chapter 8, there's a detailed discussion of the relationship between these two, and they're very important in terms of starting a design. The stator of the PM brushless machine, no matter whether it's a 6-step or a synchronous type, AC synchronous type, has 3 phases or more. You could have 6 phases or 9 phases. Sometimes a dual inverter, dual or triple bridges are used to share the current in the lead wires, and also to share the current in the transistors in the bridges. The phase or line-to-line output voltage shapes are either square wave or sine wave or anything in between, depending on the nature of the flux linkage. As we've said, the slot pole ratio, winding pitch, the pole arc, those parameters will vary the shape. The useful flux linkage equation for initial design, this is a very important formula for this allows you to make the turns per coil calculation estimates quite easy, assuming that K sub E is approximately equal to K sub T. Then you use this relationship of Z is the total number of conductors, active conductors in the stator, and P is the number of poles, and of course then we have the active flux per pole. And this assumes one parallel circuit path. If you have to have 2 parallel circuit paths, you have to put 2 or 3 or whatever in the denominator. And so we'll see how we're going to use this formula. We've repeated our formula here again, and K sub T is a total. K sub T uses a total usable flux from the magnets times the total stator conductor, useful stator conductors, and times a constant. Everything else in there is a constant. The flux equals the magnetic flux density produced by the magnets in the air gap times the flux density times the area of the poles of the magnets. So from this relationship we can conclude that more magnet flux means fewer turns per phase. That's what this tells it. If the flux is higher, the Z's are less. Okay, so if the current density is too high, we need fewer turns, so we produce more flux somehow, so we need fewer turns. So in the same winding space we can use bigger wire. That's the logic. So same number of turns per phase for coil. If you use a weaker grade magnet, you got to have more area. If you change magnets and the flux density goes down, remember flux equals flux density times area. So that means that if the magnet's weak, you need more area of the magnet. Now these pictures here show the effects of the magnet area is quite large compared to the air gap area. This is a piece of soft iron that focuses the flux. It gives you a higher flux density. For example, you could use a very low flux density magnet, a ceramic grade that has 0.4 Tesla flux density, but because of the ratio of these two surface areas, you multiply that times 4 and you can actually get 1 Tesla in the air gap using a 0.4 Tesla magnet. Here's another example of flux concentrator. This area here is much less than this area here, so you get a higher flux in the gap than the magnet. Now internal IPMs are a little bit different, similar but different. The magnets are here's the stator coils, and here's the magnets, and here's the salience in between. So both of these magnets provide the flux. So the flux is this area plus this area times the flux density of magnet. That's the magnet flux. Here's another example of that. This is the Prius motor. As you can see, it's the stator's got 48 slots, 8 poles. The magnets are V-shaped, and these pieces here are soft iron between the magnets, and there's some leakage support webs here and here. Where does the flux go? It goes this way, and we'll see some finite element plots of that later. The torque component, the next slide we're going to look at the torque component from the magnets and the torque component from the saliency, and you see that here. Here's the formula for the magnet torque or alignment torque that gives you this torque here, and here's the formula for the reluctance torque, which is this torque here. So where these two are maximum, where they overlap here, so if you add these two components together, that's the resultant torque, the total torque you get in the machine, and you can calculate those from these two formulas. The IPM equivalent circuit looks like this. This is the D-axis equivalent circuit, and this one is the Q-axis equivalent circuit. Here's a comparison of the air gap flux versus the magnet grade, and you can see here, this is courtesy of Don Novotny and Tom Johns from the University of Wisconsin, and this is a BH curve of a magnet where a ferrite magnet has been plotted on here, and a rare earth magnet has been plotted on here. So 1 Tesla versus about 0.4 Tesla here. And as you can see, if our operating load point is this line here, which is the permeance line, another way of defining that we've already discussed, but we can mention it again, is if you plot the air gap on the H-axis and the thickness of the magnet on the B-axis and project lines over to that, where they intersect would be the line intercept of the permeance of the air gap, the magnet versus the air gap thickness. You draw the load line to go through that point and continue it on up until it intersects whatever magnet plot you're looking at, and then project that over to here, and that's the flux you get. So the and if you move that line over to determine what the demagnetizing current is, you see. So this is the PM demagnetization curve and air gap load line for rare earth and ferrite, and you can see the advantage of the higher flux magnet material. This is at 1 temperature, I should point out. We'll talk about that later. The torque and voltage relationship for brushless permanent magnet machines that we talked about, the torque constant and the voltage constant are approximately equal. This looks like a repeated slide here. The peak motor voltage constant based on the peak flux linkage per phase is peak flux linkage equals the number of phases times the flux per pole. This becomes the average phase EMF during 120-degree commutation. For line-to-line EMF, there are 2 phases in series, so taking into account that each phase coil has 2 sides which are linked by the flux equation, the equation for the peak case of E or back EMF becomes this. So our formula we showed before looks like this. These are winding factors and flux linkage factors, and so this 2/3 here is because we're only using 2/3 of the Z, the number of conductors. Z is the turns per coil times the number of coil times 2, because there's 2 sides to each coil, and this is the flux in the gap per pole, and this is the number of poles. If you're talking about a unipolar machine or a delta connected machine, this 2/3 is replaced by 1/3. For the PMAC synchronous motor, this relationship doesn't hold exactly true for a couple of reasons, but it's very close and very useful for first approximations for the design process. But frequently in servo systems, these torque constant numbers were very important and used to determine in the control algorithms and the controls. The case of T was one of the servo system transfer functions, and that value was used to multiply times current to determine the torque applied to the load. But you have to be careful about doing that with a sinusoidal machine. You have to correct the case of T value depending on how it's defined and what the shape of the back EMF looks like in the with the AC version of this. And I guess, as we know, any PM machine can be operated as a generator. This generator can have surface magnets or embedded magnets. The only difference is the power flow is reversed. It goes from motoring to generating instead of it's driven, it's motored, it's driven, so the power is reversed. The prime mover supplies the driving torque, and the back EMF proportional to RPM is produced from on the line-to-line terminals. The output voltages of each line-to-line leads can be rectified using a simple diode bridge or an active transistor rectifier circuit. Voltage regulation can be initiated by precisely controlling the speed of the prime mover, because we know that the output voltage of the PM generator is directly proportional to speed. To control the voltage, you would have to regulate the speed. So as the load increased, due to the voltage drop you would get from the generator, you'd have to increase the speed to maintain a constant voltage, and that is not easily done. So using prime mover speed control for voltage regulation of a generator is seldom used. If a simple diode rectifier is used on the output of the generator, then a down chopper is usually used to regulate voltage. You design the generator to have higher output voltage than you want to regulate to, and use a down chopper to regulate the DC voltage. Of course, you need caps across the output to smooth it out, smoothing capacitors. But if a active transistor bridge rectification is going to be used, then you design the generator to have an output voltage lower than what you want to regulate at, the value you want to regulate at, so you boost the voltage, and the voltage can be boosted as much as 100% by this method, I'm told. For generators, there's different load types. There's open circuit condition of the generator, that gives you the maximum voltage. Then there's short circuit loads, infinite bus, that's on the grid, diode rectification, passive impedance, and active rectifier. For diode rectifier with the down chopper, for the regulation of the EMF is designed to be 50%, 25 to 50% higher, as I said before, than the regulated voltage. For active transistor, the output of the generator can be 25 to 50% lower than the regulated DC voltage, as I said in the last slide. Surface PM generators exhibit the lowest voltage drop with load. IPM generators can exhibit considerable voltage drop reload as a function of load. Any permanent magnet motor will become a generator if it's commutated 180 degrees electrical from its motoring commutation. A permanent magnet synchronous generator regulation with diode rectification, the direct inductive resistive load or DC output regulated with transistor type down chopper. Here's our voltage and current relationships here. The active transistor bridge rectifier, the circuit looks like this. It looks just like a regular motor circuit. And the beauty of this type of regulation system, that if you have a prime mover that if you have a prime mover that needs starting or cranking, then you can use this type of a regulator as a motor drive inverter to use the generator as a starter. This is done for jet engines for sure. The permanent magnet generator load power factor and regulation. Here's the wind turbine application, permanent magnet generator connected with infinite bus, and here's a set of voltage regulation curves typical with a lagging power factor. The formulas for the output power. For more rigorous discussion of this performance connected to different loads, see Chapter 9 in this book. Here's what happens with the torque production of a square wave driven brushless motor, 3-phase with only 2 phases conducting at a time. This is a case where the three phases are Y connected, and each one is connected in according to, each one has an H bridge on the phase, and this is the torque production scheme. So that concludes this lecture.